Hi, welcome to the second part of the mechanics tree videos on circular motion. This time we'll be looking at vertical circular motion. Now, key point here is, because it's going round in a circle, well, that's not a very good circle, vertically, angular speed is not now constant. Okay, so there are two components of acceleration. There's acceleration towards centre, still v squared over r, and an acceleration instead of the normal linear speed v that we had there. Okay, that's now a function of time. Key to tackling vertical circular motion is using conservation of energy. So let's have a little look at that, shall we? Okay. Small bead threaded onto a smooth circular wire, so the bead cannot leave the circle. That's a very important point we'll be going over again in a minute. Okay, so bead, smooth wire, can't leave the circle, released from rest up here, find its speed as it goes wee, as it reaches this point L here, find its speed and the force exerted by the wire on B at that point. So, well, at point B, you're releasing it from rest. So the energy there is potential. So you've got the potential energy from B down to L is all going into kinetic energy at L. Okay? If you take this as a zero potential energy level, the change in potential energy from B to L is the kinetic energy at L. So work out the height, which is obviously the radius here, and this distance of height here is 60 cos r, the radius, and that equals half mv squared. So work that out, rearrange it, and you get the velocity as root 3gr. Now, using F equals ma at point L, obviously towards the centre, R minus mg is ma, we're using that expression for A, so R minus mg equals 3mg, R equals 4mg. So all we've done is use difference in potential energy to kinetic energy, and then F equals ma towards the centre. Okay, so other situations. The bead on a wire could not leave the circle. In these cases, the object can. So you'd probably be looking at a particle on the end of a piece of string. Now the key is, when it gets up to the top here, to describe a complete circle, it must, at that top, the string must be taut, okay? So that there's a force and the acceleration towards centre. You retain circular motion if there is an acceleration towards the centre. So all you look at doing is, at the top, have the condition that t must be greater than 0 and incorporate that into your equations. Okay, now that's if it completes full circles. What about if it doesn't? Well, so you've got the option, it makes it to B and all the way round completes. What if, most of the time it'll be projected from bottom here, what if it just gets to here and goes, not enough energy, no more energy, come down to here, and then obviously it would just be going back and forth like so. Okay, so it can get above the central point, up to here, and from that point down to where the string becomes taut again, you're counting it as just a simple projectile. Or it might not even have the energy to get up to C, it might just go back and forth and back and forth like a little pendulum down here. Okay, so key points for those are, at the point here when it leaves the circle, the tension in the string will become 0, and the key point for this one is obviously at its highest point there, velocity will be 0. Alright, little example for you. Okay, this particle can leave the circle. Light inextensible string, tells you its length, mass of the particle. Classic exam question. It starts at the bottom, is projected with a certain speed. Find the least speed if it's to complete a full circle. So we want it to get up to there and just have the energy just go all the way around. Okay. So at the bottom has kinetic energy. At the top, hopefully, has kinetic energy if it's to complete a full circle, and there's obviously energy-wise been a gain in potential. So you can just simply equate those and get this equation, and then cancel m's, do some working out and rearranging, and you get V as 2.48 meters per second. Okay, calculate the tension in the string at this instant. F equals ma at the top of the circle. Obviously at that top point there you've got mg plus t equals m v squared over r. Remember, we're using that instead of a. Sub all that in, you know the mass, you know V at that point because you just worked it out, and you know R, so you can get D as 2.25 newtons.